Well, solar and storage is the talk for tonight. Tom Guttormson is the principal technology engineer, at Connexus. He played a major role in making this all happen. And I was so glad when he agreed to do it, because it's something that I just really wanted to share with more people. As far as I can see, it's a leading thing going on in our part of the country. So, Tom, why don't you just take it and go from there, okay?
Sure, very good. Thank you. So I'm going to screen share again here. So thank you all for the invitation to speak to you today about this project, the system that we have in place. I hope that it's informative. I hope that it's educational, and maybe a little bit of entertaining along the way. We'll see how that goes. So yeah, solar plus storage, from concept to implementation and operations. So this site is in operations. It has been for 3.5 years. And I'm going to walk through what it is, what we're doing and why, how we got here, and how this thing works. So just a little bit about Connexus Energy. We are a member-owned distribution cooperative located north of the Twin Cities, north and to the northwest, and encompass the northern tier suburbs in Minneapolis-St. Paul. We are the largest co-op in the state of Minnesota, one of the largest in the nation. We have about roughly 1,000 square miles of service territory and about 135,000 members, at least at this point in time. So you can see where we are on the map there in Minnesota. So in terms of renewables, we actually have 5 different sites. We have our 240 kilowatt solar garden that's in the front yard of our office space in Ramsey. And we have these 2 sites, solar plus storage, one in Ramsey, of which the field tour was at, another one in Athens, about 2 miles south of the city of Isanti. Then we also have 2 other just solar without battery installations, and they are single tracking solar systems, one up just south of Princeton, and the other one is just to the northwest of St. Francis. So that ends up being 20 megawatt capacity total of solar, and the batteries at the 2 sites of Ramsey and Athens totals 15 megawatts of grid scale capacity, 2-hour batteries, so that would be 30 megawatt hours of energy. And those are the 2 systems we're going to focus on today and what this slide deck will cover. So here again is our capacity for the solar plus storage. Now this picture of solar, that's actually from our solar garden in front of our office building. You can see some pollinator habitat there. And the batteries to the left bottom of the screen is actually a bird's eye shot of the storage facilities at the Ramsey site, which is what we visited not too long ago. So what are we doing? You can do a lot of things with batteries. Wouldn't it be nice if we had big batteries on all of our wind turbines out there so we could store all that energy and pull at it when we want to? Technology quite isn't there today, but hopefully we're moving in the right direction. This particular project is one where we put the batteries in for economic purposes, specifically for demand response under peak load conditions. So the grid doesn't need the batteries. We have plenty of capacity. This is an economics problem. So what we did, first built the solar system. Well, we built it all at the same time. The solar system can stand on its own. So we built the solar facilities, and that ties and feeds directly into the distribution grid. So that serves members. Then we built the battery site. Now the batteries needs the solar, and I'll go into some of the contractual obligations for this in a little bit. But what we do is when we want to dispatch the batteries for demand response, we charge the batteries from the solar system. And then when we're hitting the peak time of day, we dispatch the batteries, dispatching that energy out into the grid, therefore lowering our grid load during peak time. And basically what that does is shift. So we're generating the energy in the morning, charging the batteries up during the day, storing that energy through the day, and then discharging that solar generated stored energy later in the day, shifting the energy from when there wasn't as much demand to the part of the day when there is the most demand, thereby lowering the total system demand. And that is an economics problem. We are charged for peak energy usage or peak demand, if you will, during the highest usage hour of the month. So that's when we target to dispatch these batteries across that 1 hour when we get the most demand charge, the most expensive time for us to operate, thereby reducing our costs. And since we're member owned, that essentially is passed on to our members. So how do we build something like this? 3 key aspects. One is you have to have some land in order to build this on. The Ramsey site is 17 acres. The Athens site is 40 acres. Most of that, of course, taken up by solar panels. And then where you put the land, you've got to have some permitting capability. Where we permitted these sites, there was not any language in the cities and the counties and the jurisdictions that really spoke to being able to permit this. So we had to work together with our local governing authorities to come up with proper permitting language so that we could do that. And then, of course, you have to tie into a place in the distribution grid, electrical grid, where it can take all that energy that's discharged from the solar plus the storage and be able to use it without overloading anything and developing power quality problems and that type of thing. So that is step number 1. Oh, I meant to mention back on this site here too, another key driver, not just the economics, that's a key part of it, but from our members really want 3 things, 3 R's: rates, which is what? Economics, reliability, and when we built these systems, we promised everybody we wouldn't break the grid by building it. Rates, reliability, and renewables. But in order to do the renewables effectively, go back and see number 1 and 2, rates and reliability. Don't break the grid, and make sure we do it in an economic manner. So with that, this is all done in such a way that we don't raise the rates. It doesn't put upward pressure on rates. It actually helps reduce the cost and thereby make our rates more stable. Wanted to throw that in there. So sorry, I went backwards on it. So now let's move ahead again. In terms of permitting, land acquisition, and being able to interconnect to the distribution grid in such a way that it is feasible technology-wise. So here's how we built this. It costs a lot of money to build this, and it takes a lot of resource and expertise. So what we did is partnered with solar and storage experts. So we partnered with a solar company. It was Socor at the time, purchased and now owned by Engie. So we have a power purchase agreement with Engie. Engie put up the capital and built the site, and they own the solar facility. We purchased the power from the solar facility via a power purchase agreement. It's a 25-year contract, so we will continue to purchase energy from that site for that duration. Then the storage, same thing. We partnered with NextEra, which is a subsidiary of Florida Power and Light. They have storage and all different kinds of renewable, including wind and solar facilities across the nation. And this is a little bit one of the first of its kind that they built with us, with the solar plus storage for the demand response. Also, again, the contract here, a 25-year term. And how this is set up is a storage service agreement. So the energy going into the batteries, we've already purchased from the solar system. Now we're just storing it. So basically, it's a rental fee for us to store our electrons in their garage and let us take them out and use them when we want for our demand reduction purposes. And so there's a monthly fee, not based on how much energy is in there or not, just based on being able to use the facilities. So a couple of shots from above. This is our Ramsey site. Again, I mentioned that this is about 16, 17 acres. You can see there that most of that, of course, is the solar facilities. And on the bottom right, you can see where the battery containers are. and where what we call the interconnection gear is. That is the inverters to change the DC output from the solar panels to AC, transformer to the right voltage, and interconnect it into the grid and connect it up to the batteries. And this is just off of Highway 10, just off of Armstrong Boulevard. Then the Athens site, a couple miles south of the city of Isanti. Along the right there is University Avenue, and on the left you can see the solar facility. This is about 40 acres. And the output here, the total output for solar is 6.6 megawatts and 9 megawatts of battery storage. This is actually two different systems just located on the same property. The northern 2/3 of the panels and 6 out of the 9 battery containers are connected into a distribution line that goes to the north, connected to what we call our Isanti substation. And the southern 1/3 of the panels and 3 of the battery containers are connected into a distribution line that feeds to the south into what we call our Cooper's Corner substation. Those two facilities are operated completely independent of each other. They're just located all on the same facility. So essentially, from an operations point of view, we call it 2 sites. So with that, the Ramsey plus the Athens, we actually have 3 different interconnections and 3 sites that we operate. Now, for you engineers and technical people out here, this is a very simple 1-line diagram of the facilities. And this is the same for all 3 of the interconnections. So let me start with the solar. You can see on the top left, the green. I don't show the panels on here other than a box for a solar array. And the array generates power to a voltage up to 1500 volts. And it goes to the, excuse me, to the inverters and changes the 1500 volt DC to 600 volts AC. And then that feeds over to the step-up transformer, and that transforms the voltage up to 12.5 kilovolts or 12.47, which is what our distribution grid voltage is. Then we can see the delivery meter right there, M2. That is the cash register. So that meters all of the energy generated by solar, and that is the meter that is used to determine how much solar was generated and what Connexus Energy purchases. And so all the billing on a per month basis is done from that information. Then we go through a photovoltaic recloser. It's basically a big circuit breaker that sits on the ground. And that circuit breaker can trip if there's a problem, or it can be opened up to isolate the solar from the rest of the system. Connexus Energy has permissions and capability to trip that recloser open if we need. And then when it's okay for it to be closed, then ENGIE has the capability to reclose it and put the system back in service. Then we go to the last green box. We call that our point of interconnection. So basically, that's a giant wire nut. It connects the cables from the solar recloser and the cables from the battery system to the cables for Connexus Energy, which I'll talk about in just a moment. But that piece right there is where all 3 components, solar, storage, and utility, are all joined together. Now, over on the right, ES array, energy storage array. That is the batteries. Each one of those battery containers is 1 megawatt capacity, 2 hours or 2 megawatt hours. On the Ramsey site, which we visited, there are 6 containers, therefore 6 megawatts of capacity, 12 megawatt hours of total energy. And that goes also through a series of inverters that change the output from 1500 volts DC to 600 volts AC, up through a series of transformers, again to the distribution grid voltage, again through a recloser, again a pad mounted circuit breaker, and that can be tripped to isolate the batteries from the rest of the system, through a disconnect switch, and then cables over again to this giant wire nut, the 3-way junction box. And then from there, we have cables that steps into what we call the interconnection meter. Now that is a meter, but we use that more for operational monitoring and energy archiving than anything else. We don't use it for billing. is basically a point of operational information. And then we go through a master switch. Again, that's a big pad mounted circuit breaker on the ground. And that Connexus owns and has control of to trip and close to either take the site offline, the entire site, or put it back in service. From there, we have cables that goes out to a switch next to the road, and that ties it into the actual operating distribution grid. Now, look at the colors. Green is owned by Engie, red is owned by NextEra, black is owned by Connexus Energy. One of the some of the contractual obligations here are that all of the energy stored in the batteries needs to come from solar generation, not from the grid. So how we set this up is, of course, with the ITC, the tax credit that's allotted from the government. That is one of the requirements, that all of the storage energy has to be from solar. And the other part of that is none of it can flow through utility-owned facilities. So how we set this up is the green equipment is all owned by Engie, including that solar direct coupling point. And the cables going through that connection cabinet to Connexus Energy's first box is also owned by Engie. The red is all owned by NextEra. And of course, the black is owned by the utility, Connexus Energy. And the way this works is when we want to charge those batteries up, we will send a signal to the batteries, time to charge, and they will start charging up equal at a rate that's equal to solar generation. There's a communications cable that goes from that solar delivery meter over to the battery controls that provides telemetry information to the battery controls as to what the solar generation is. And the battery controls will monitor the rate of charge to equal the solar output. Therefore, when we're charging, all the solar generation goes into the batteries. None of it goes to the grid. And there's no grid energy, or there's no energy coming from the grid into the batteries either. That interconnection meter basically reads 0 when we're charging the batteries. Once the batteries are all charged up, the batteries say, controls say, okay, we're done charging, and then the solar proceeds to go back out onto the grid. So that's why we set this up this way, to have NextEra be able to get that tax credit. And of course, that credit goes into the economics of how much they need to charge us for renting the storage space. So that economics is favorable for everybody. That was kind of a mouthful on that. I hope that made sense, but those are a couple of key factors as to why we built the system the way we did. Now, somebody might say, why didn't you DC couple the solar and the storage? At the time, we wanted to make sure we got the solar built for planning the batteries. But in case something got delayed with some of the technology, this is all new stuff, we wanted those to be a little bit independent so we could make sure we had the solar built and tested and up and running first before the batteries were completely ready. And then it also allowed us to go out to, and do a request for bids for best of breed, if you will, best pricing. And in order to do that, it made more sense to do the AC coupling. So that's why we ended up with AC rather than DC coupling. Okay, spent a lot of time on that. Let's move on to the next part here. So let's talk a little bit about study. What does it take to connect this much facility with that much output into the distribution grid? So for those of you engineers, if there are any, we interconnected these facilities almost at the tail end of live active distribution feeders. So we wanted to make sure that our interconnection at that point and the operation of the grid was able to handle that much power output into an active grid and not cause any power issues, or power quality issues, or reliability issues, and that type of thing. Now, we had never done this before, but we want to know how to do this. So we decided, let's do this internally. And we developed a process using the study tools that we have in order to study the various aspects of this to make sure this is feasible. And then we also hired an independent consultant. And we asked them, here's our facility. Here's how we're going to operate this. Here's where we're connecting it. You go and do your study your way with your own tools, and let's see how the results come out. So we did that, and the numbers and all the study indicated from both sides that yes, this will work. We can do this, and the results were almost identical. And it turns out they did use the same process we did, or we used the same process they did. And that worked out really well. There was one part of it they said would not work. Our system said it would work. And I thought, well, how are we going to manage this? So for you engineers, you think about this, you have a lot of power being dispatched from batteries and solar at the same time onto the tail end of a distribution feeder. So that power is going to reverse feed the feeder back to the substation, and the substation voltage is regulated. So what that's going to do is push the voltage too high out at the solar plus storage site. So we use some capabilities in the inverters to do what's called VAR compensation, use reactive power and consume reactive power from the grid in order to control voltage. For those of you that aren't engineers, I'm not going to go into the physics of that, but for those of you who are, and if you understand reactive power, you might have some understanding as to how that worked. Our study said that would work. The consultants said that it would not. I thought, well, we're going to build this. I believe our study. Let's try it. And so we got everything set up. I did have a backup solution in case that didn't work, but I wanted it to work. And we tested it, and I was absolutely amazed when we ran this thing for the first time and tested those results. The actual field conditions and the values that we measured in the field were spot on to the system model that our engineering group built. So that was, for me personally, that was a very fun outcome. So anyway, we studied to make sure we had sufficient capacity in all the wires and equipment. We studied to make sure that if there was an outage, this thing would shut down and not feed out into the distribution grid, and that it would be able to handle any outages from the system or would not cause any issues. We tested the voltages, studied the voltages, and we studied to make sure we weren't putting any bad harmonics out onto the system that would cause any neighboring members or customers any issues, and that turned out real good. So that's how we did the study. The first time for us, it was challenging. It was a lot of fun, and we ended up with a very good result. So now we've got 3 different entities, and all these things have to work together to accomplish what our operational goals are. So here are some constructs in terms of operating agreements, contracts, and that type of thing, how we set this all up. So starting with solar, remember back from the one-line diagram that the solar facilities directly connects to the utility facilities. So ENGIE did all of their solar design, they did all the purchasing, all the construction, and they do all the maintenance. We did all of the same, the design, the funding of equipment, and the installation of all the interconnection equipment, the recloser, the meter, the cabling, and all that stuff that connected up to that 3-way connection cabinet. And so we established an interconnection agreement with ENGIE because Connexus and ENGIE are directly physically coupled. Now we need something that also defines the same types of things with Nextera that's in an interconnection agreement, but we're not connected physically to them. So we developed a 3-way operating agreement, and that was developed mostly by Connexus. It was we had a lot of input and collaboration with Nextera and ENGIE on putting that together, and that establishes all of the operating procedures, the safety procedures, who communicates to who for what different conditions, and all those types of things, and the requirements for how you operate this and what some of the thresholds and stuff are. So we all know who's doing what for what purpose and how all 3 of these entities work together to make this as a whole system work together. So that worked out very well in the end. It took a little while to get there. A lot of things to weed through with technical terms and conditions and operating constraints and all that type of thing, but worked out really well, and we have a good agreement today. So that's how that was all set up. Again, I previously talked about power purchase agreement with NG, the energy storage agreement with NextEra. Here's a couple of pictures of what this looks like. This is the Athens site. And again, there are 9 1-megawatt battery storage containers there. On the left, you can see the solar array spread out over the 40 acres. You can't see the southernmost part of it, but you could see a good chunk of it. You can see the left there are concrete foundations for putting the batteries on. And the small little gray boxes just to the right of that piece of equipment, orange piece of equipment, those are the inverters. They're string inverters. They are 125 kilowatt inverters per unit, and they're all ganged together. So it's not one great big inverter, and it's not a micro inverter on each solar panel. It's string inverters. So if one of them goes out, of course, you still have all the other ones working. And it's not having to deal with one inverter on each panel. So that design for this facility worked out very well. Then you can see the transformers on the Athens site. There are 4 transformers, one for the smaller system that's Cooper's Corner, and 3 for the other system that ties into our Isani substation, the 6.6 megawatt facility. Then over on the right, you can see the storage containers, 9 of them there, and how they all are lined up. You can't see these from the road. It's far enough of University Avenue that you can maybe get a glimpse of the solar panels, but you really can't see the rest of the facility. So timeline on this, we started planning for this in the middle of 2016. So that's where we did our strategy. How can we do this? What are some of the ins and outs of being able to do this? Is it feasible? And from a business standpoint, does this make sense? Can we save money? And can the partners make money so that we're all economically whole? So then we went through a site selection. And interesting in the site selection, the first 2 sites that we picked out did not work. One of them was actually in an area we thought would be very suitable because it was on a construction landfill, but it was still fairly close to a nice residential neighborhood. And that just did not work out really well in that area. So we had to evacuate that one. So we ended up with 2 sites that worked out very, very well, but we did go through a reselection of sites, if you will, in this process. So we had a consulting partner develop a request for proposal for us and with us for both the solar and the storage. Went through that whole procurement process of selecting partners and going through and doing all the detailed design. We started construction in the 3rd quarter of 2018, finished the construction in the 3rd quarter, we did construction through actually 2nd and 3rd quarter of 2018, finished construction in the 4th quarter of 2018, the early part of it, and then spent the rest of those 2 or 3 months actually testing the facilities, the solar and the storage. And our target was to have this all done, tested, and fully operational by the end of the year. And we made it. Not with a lot of time left, but we did make it. We actually commissioned that site and put it into commercial operation. We finished testing on December 22nd, and wrote out the permission to operate letter on December 23rd. And it's been in service ever since then. So this is a couple of interesting graphs that's taken right from our system that monitors the output of this facility. So this is a day back in 2019 when we're going to dispatch those batteries. So we have an internal process built by our internal staff where we can use the information that we put together and also use indicators and information from our power supplier, Great River Energy, as to when that peak day is going to occur. And then we do some focused looking to see when we think that one peak hour is going to be on that peak day and focus our operations around that. So this was a June day back in 2019. Now, the lines here, the orange line represents irradiance of sunlight. So it's a nice sunny day. And we think it's going to be a peak around between 5 and 7 p.m. So we schedule these batteries to charge up. We can actually schedule them a day ahead of time. And then the following day, right away, as soon as the sun comes up in the morning, they'll start charging. The blue line is the flow of power into and out of the batteries. And the green line, the purple line is the solar generation. So you can see the sun comes up, got a nice sunny day, and we reach a maximum solar generation throughout the whole day. And you can see on the bottom here, this blue line, the batteries are taking that solar energy in and charging up the batteries. Then they come to a point right here where the batteries are all charged up. And so now the batteries go and they just rest for the rest of the day. And we schedule them to dispatch starting at 5 p.m. and finish dispatching at 7 p.m. They're 2-hour batteries, so that would dispense everything that's charged up. So right just before 5 p.m., there's actually a 90-second ramp up time from when they start discharging until they're fully discharging is 90 seconds. So they start discharging, and you can see right here, they discharged at full throttle, full output, 6 megawatts for 2 hours. And then we get to the end of our control period, and then they ramp back down, and they're just about out of gas at that time anyway, and they go into a resting state. So here you can see the green line is the total energy out from the site, which is the purple line, the solar, plus what's coming off the batteries, the storage, and that's our total power going out onto the grid. So that is the amount of power right there, that green line, of how much load we reduced off the grid by having solar generation and storage delivery at the same time. Now, the next day, we come in and those batteries are empty. One thing I'll mention about the batteries is those are lithium-ion iron batteries. They don't like to be completely empty, and they don't like to be completely full. The ideal spot for a resting state of charge for these batteries is 30%. We've contracted with Nextera to keep them at a resting state of charge of 50%. Not quite as good as 30, but it's still pretty good. And anything above a 50% state of charge, then you start losing more life in the batteries. So a couple of operational details here. We maintain a resting state of charge not greater than 50%. We have a limited number of these cycles that we could do per year, 75 cycles per year. And then we're not supposed to keep them charged above 50% for any longer than 24 hours in a single time. These three items helps to provide some longer life in the batteries, not wear them out quite as fast, which goes into the economic factor of what Nextera has to pay for, but still gives us enough operating ability and room, if you will, to meet what our demands are for how many time we need to operate this over the year. So that all works out. So that's a little bit about more contractual obligations with this. So the following day, again, after we discharge them, they'll charge back up. Now this day, the second day, we needed to operate again. It's another hot day. Which one's going to be the peak day that we're going to get charged or demand charged for? Well, it could be either one of them. So we have to operate on both days to make sure that we cover that 1 hour. So they charged from empty to full by probably about 1 o'clock in the afternoon. And then they sat there and rested all day again. And again at 5 p.m., it's time to dispatch. So the batteries will ramp up, deliver the energy for the control period, and then shut down. Now this one here, you can see that it started reducing its output a little bit early. And that's been an ongoing challenge with these batteries is when we run them full throttle, foot on the floor, they start to lose a little bit of capacity and degrade a little bit towards the end of their second hour. Still working on that. If we spread this over 3 hours at a reduced rate, pretty solid. But we just noticed that on that one day. And then the following day after that, again, they are empty now once we dispatched. So the following day, the sun comes up and we get a radiance and the battery charges up now to its resting state of 50%. And then it just quits charging and goes into a state of rest. So when we dispatch this, all we do is the day before, we send a signal, a couple of clicks of a mouse to turn the batteries on the following day. At midnight, they turn themselves on. When the sun comes up, they charge up. We then put a schedule in as to when we want to discharge them during that day. Then they'll discharge. And when they're discharged, the following operation to recharge back up to 50% again the next day, that's all automated. So we tell them when to turn on, and we enter a schedule, and that's all we do. The rest of this whole process is fully automated. It's pretty neat. Oh yeah, winter time. Let's see how much time we have. I'm almost done here. What happens in the wintertime in Minnesota? Well, we have our wintertime peak loads when it's really, really cold. Well, it gets really, really cold when the cold front moves in after a warm front. And when the cold front moves in after said warm front, it delivers snow and piles snow on top of the solar panels. Well, that's when we need those solar panels to generate energy to put into the batteries so we have a fully charged battery to discharge over the peak load that day. This doesn't work really good. So we came up with a little process to do some snow cleaning. This is a winter of 2018 and 19. We had a lot of snow. You remember Snowmageddon? Pile those panels full. And we had almost a month when there was no generation whatsoever, nothing we could do about it. So the following year, we developed a process to do some snow clearing. So there's two stages to this. One is, you can see we've got this ground mounted snowblower. It's a skid steer on tracks with a great big snowblower on it. If there's snow piled up at the base of the panels, just that snow drift by itself can impede self-clearing off the panels because there's no place for the snow to fall off the panels. So we'll take that snowblower and go along the base of the panels and blow that snow underneath the adjacent row to clear this so the new snow has some room to fall off the panels. That helps actually quite a bit. You can see the snowblower up there going. That does not look like a very fun job, by the way. Then, after that, actually doing that also then produces a path by which we can run that machine again. And what we do is mount a blower on that same machine that has nozzles pointing out to blow the snow off the panels. Now, if the snow is really thick and packed on and has ice, it doesn't work really well. But if we go out there after, say, our 2 or 3 or 4 inch snowfall, that blower is actually effective enough to at least get some panels showing. So when the sun does come out, it accelerates the rest of the self-cleaning of the panels and allows us to get some accelerated charging into the battery, hopefully enough energy to be ready for dispatch. So here you can see Anoka, and this isn't a very good video. This will jump around a little bit, but you'll be able to see a machine coming over here, the blower on it, and he's blowing snow off those panels. There's like 2 inches of snow there. And it's a loose enough snow, we can actually take this blower and get at least a good chunk of it off. So when that's done, you can see on the left before blowing and on the right after blowing. That was enough to accelerate charging of the solar in order to get charge into the batteries that we otherwise may not have gotten had we left the snow on those panels on a really cold day. Well, that really is a highlight overview of this project. So that has taken you through its initial concept, why we wanted to do it, what some of our strategies were, what it took to build this thing, how long it took to put it in service, and at the end of the day, we've got an operating system. And to pull something off like that, it practically takes a village. I can't say enough about the relationships that we developed with our partners, Engie and Nextera, and then just a multitude of people in our engineering group, our SCADA, system control data acquisition, our IT department and metering department. There's some metering challenges with this. Our whole construction and maintenance team, all of this in order to pull this project off and make it happen. And then we developed another group called DSO, Distribution System Operation. And that is a group of people where we look at forecasting our loads, monitoring the systems to make sure they're all up and running, working conjointly with our solar and storage partners to make sure the assets are working, and just working together as a team to pull us off and get the savings that we're looking for every month. So thanks to the Connexus team and our partners. So somebody mentioned when we started too about pollinator habitat. This is a picture of our solar garden out front of our office space, and you can see a lot of wildflowers and pollinator habitat. That was from prairie restorations at the time. We did that initially because we really weren't sure what we wanted to put in there. Grass, you have to maintain that. Rock, you got to weed that, and it's hard. What do we do? Well, let's put in some wildflowers and pollinator habitat and make it look like prairie, and we'll put a nice black fence around it all, and it looked pretty good. One of our employees said, gee, can I put my beehives back there? And we thought, sure, why not? Well, then somebody else got a hold of that idea, a commercial beekeeper, and they said, can we put our bees back there? And they did. And that worked out really well. They got some really good honey. We partnered with that bee developer and had beehives there for a number of years. And now we are doing this at all of our sites. And it wasn't too long before we started getting calls from newspapers and National Geographic and different people, University of Minnesota. Everybody was very interested in this. So it's really fun to see this take off, and what a nice dual benefit. Now, somebody mentioned, Chris, you mentioned the other day, we had some livestock in there. We had somebody with some sheep come in and let them browse around for a little bit. It was just a one day, just a trial. But the sheep were happy. They had a lot of good grass to eat, and helped mow down some area underneath the panels. And so that's something that is also a plausible thing to do in these areas where the panels, they take up some real estate, but we can get some dual benefits by pollinator habitat, or use it for livestock, or that type of thing. So it's very exciting to see those types of things take off with these types of installations to supplement their usage. That is the end of the prepared presentation. And it looks like we're at 6:45. So with that, do we open this up for questions?
Yes, we definitely do. I saw some people sending some questions through. Tom, let me just ask you this question to start it out. I mean, it looks like you guys did an amazing job, really, really amazing. But if the old story question is, if you were to do it again, would you do anything different?
Oh boy, I wasn't prepared for that question. Short answer, I'm sure, has to be yes, because when you do something the first time, you learn lots of things and you do it better the second time around. But really, I'm amazed. It just turned out really well. I cannot say enough about what it takes to communicate as a team, to have a well laid out project plan, and good relationships with your partners, that you all have a common understanding, and safety has to be number one. So we did have one unfortunate incident through the project. Everything turned out fine. But it was a scary event, and we really shored up some of our safety processes. So that was a good outcome at the end. So I could probably go through and find a lot of details as to what we would do better. But really, for the overall process, it would probably be very similar.
Okay. What about, a lot of people nowadays that are putting in gardens are putting in tracking panels.
Yes.
And would you consider that to be feasible for this type of thing?
Actually, that's a very good question. And yes, it is. Now, I spent time talking about the demand response economic benefit of this system. As you saw in, let me go back to this slide right here. Bring that back up again. So you can see the slope here on the solar starting up through the morning, flattening out during the day, and then dropping off in the evening. The tracking, the single axis tracking solar stations we put in track from east to west. So the panels are at 60 degrees facing the east in the morning, and then they flop during the day. So they're flat at noon and then tilt up to 60 degrees to the west at the end of the day. The solar rise, if you will, is a lot faster in the morning and a lot slower in the evening with a lot steeper curve. So you get a whole lot more kilowatt hour energy production through the day with the tracking panels. And for our benefit, the solar sustains itself at a higher level longer in the evening across our peak hours. So there is a definite economic benefit for us there as well. So with the trackers, of course, they're more expensive, but you do get more kilowatt hour generation at the end of the day. So you have to work out the economics of, does the cost or does the added benefits you get from added generation outweigh the additional cost you have to pay with the trackers? And because of our demand response economics, for us, the answer was yes. If it's just straight energy production, I'd have to sit down and work the pencil on that a little bit more. It might work out, but it's certainly something worthy of consideration.
Okay. Tom, can you see the chat line on your screen?
I can read those.
Oh, there it is. I can. Okay.
Yeah, or we can hand it up to Pete if he wants to ask them in person.
Didn't see that. Should I just go through these?
Yeah, let's do that.
Okay. Oh boy, how many panels are in each string, and are there DC optimizers or other powering conditions on the panels? The DC optimizers, no, there are not. How many panels are there in a string? Oh boy, I'd have to do the math. At Anoka, there are about 13,000 panels, and there are 27 inverters. And of course, when we do strings, there will be several panels in strings in a series, and then several of those series that are connected in parallel. And then you have that going on all the way up to where it's all collected together and go into the inverter. So I'd have to sit down and do the math. I honestly do not know how many panels are in one, for example, a series string. I think it's, I have to get out the drawings. I think it's maybe, oh boy, a dozen or so, 10. I'm really sorry. I don't remember that off the top of my head. I should. I didn't have that. I didn't have those numbers in front of me here. But you know what? Email me. I'll find out and I'll send it to you. How's that?
All right.
The depth and discharge and state and charge parameters for your batteries are so different than the live PO4 used in electric vehicles. Well, there's an interesting question. So the lithium ion batteries probably have some different characteristics because they're, you know, they're out there and do what they do for charging and discharging for peak, and they're not on a constant state of charge and discharge like they are a car. I really can't speak to the chemistry on that. So I'm thinking, yeah, the charge parameters probably are quite different. Now, one thing about these batteries on the site, I said that we charge them up at the same rate of what the solar generation is. That's contractual. From a feasibility standpoint, we can connect those things to the grid and turn them on and charge them up at the same rate, if you will, as to what the rating is, what the rating is. So we could connect those up to the grid and turn them on to charge full bore, and they will charge up in pretty short order when they're connected to the grid. 6 megawatts, they'll charge in 2 hours. And we've done that. We do that during testing. We'll charge from the grid specifically for testing, so they're feasible to be charged up in 2 hours for 12 megawatt hours, six megawatt batteries. But yeah, the characteristics are, I'm sure, different than they are for electric vehicles. Understand batteries are hard to monetize. Did you figure out a rate of return? Well, there's two parts to that. As I mentioned, Engie and Nextera put forth the capital to purchase and own the batteries and maintain them. And we purchase the power and have the energy storage agreement. So from Connexus Energy, where we are basically operating for OpEx and not CapEx, we had a return on investment on the first couple of months. These savings that we gained exceeded what we pay out for the purchase of the energy and the rental of the storage space. But now, for the return on investment of the CapEx part, there's a 25-year lifespan on these contracts. Of course, you need to beat that by a number of years in order to make this pay. And I don't have the financials right in front of me here as to what Engie and Nextera put up for capital on this, but I'm thinking their rate of return was probably in the neighborhood of 8 to 12 years, somewhere in there. That's the best guess without actually looking at the numbers in front of me. Now, if I'm not answering these questions correctly, or you still have some more that you want to ask about that, just please put it back in the chat box. Oh yeah, so here I've got the lithium iron phosphate batteries. I myself am not really familiar with the charging difference between the phosphate and the iron. I know that the iron is supposed to be a better chemical for using for the business application that we have. You charge them up, you let them sit there, you discharge them, you fully charge them, then let them sit there again. And I'm not sure about the chemistry of this. Why that's better than phosphate, I have to go research. Another question here. Has your strategy of partnering for solar and storage services allowed you to essentially exceed Great River Energy's limit of 5% renewables from your load? Great question. So with the solar plus storage, plus having the other two solar sites that we just built, we have 20 megawatts of solar generation, 10 megawatts of storage capacity. We have met that 5% limit. And there are times on the shoulder months when our loads are lower than they are in the wintertime, and especially when they're lower than they are in the summertime, that if we dispatched everything at one time, we would exceed our 5% limitation. And so we've essentially met that. And that's where we're at today. What happens on a very cloudy day? Oh, great question. I love this one. So those batteries on a sunny day, from empty to full, they'll be charged by noon. They charge pretty fast. On a cloudy day, especially if it's heavier clouds, maybe not raining, but heavier clouds without precip, it'll take all day to get from 50% stated charge up to full charge. So what day was it? We ran here not too long ago. I don't think it was the one earlier this week. A couple of operations ago, it was a warm day. We're going to have to operate, and it was cloudy all day. And I was wondering if we were going to get fully charged from 50% up to full, but we did, just barely, but it took all day to get there. So solar generation on a cloudy day when we don't have a lot of precip, you can figure maybe 30 or 40% of nameplate of solar generation. And that'll be enough to get us from a 50% stated charge to full, but probably not from empty to full. Any other questions? Do we hit everything here?
Tom, while people are typing, I'll ask you one. I know GRE is looking at a huge battery system going in that's supposed to be with 100-hour batteries. Based on your experience with your system, what do you think about that particular system they're going to use? Does it sound feasible, or what are your professional thoughts?
Oh,
or am I putting you on the spot?
Oh, no, not at all. The unfortunate part of that is I've had some conversations with Great River Energy on the product, but not into any depth on the technical aspects of it all. Of course, that's a completely different use case. You can see what our use case here is. We're trying to target that monthly peak for cost savings.
Right.
Now, the Form Energy battery, that's what a 1 megawatt battery for 100 hours. I might be
Yes.
getting numbers wrong on that, but it's a smaller capacity for longer duration. So a smaller output capacity, but a lot of energy. So of course, what they're trying to do is look at transmission peaking, look at MISO pricing and that type of thing. And how can they store energy when energy is cheaper and it's available, and then dispatch that out over a longer period of time to provide more economic value through longer peak hours and peak times that you're going to see on a transmission system that are different from what a distribution system peak is. And so that would be their business target for that. So it's a great start. I hope to see that develop well, and hope that over time that technology continues to be developed and refined so that can be used more and more across the grid. I'm very excited to see how that comes out.
Is that supposed to go operational in the near future?
It's still in development right now. I don't know what their time schedule is.
Okay.
To be honest,
Okay.
I don't think they've started construction on that yet. But I've actually not seen the time schedule on that, so I'm not able to answer what that is.
Okay. All right. Any other questions? Patrick Holt had a question I noticed about frost and heaving with that. Was that an issue for your system?
Frost heave actually was not. So the pilings on the solar panels are driven deep enough, they're below frost line. So frost has not had an effect, at least not that we've seen or that we really anticipate to. That's been pretty good. So they're down there pretty deep. But frost on top of the panels, that's another story. Our big bad snowblower doesn't blow the frost and the ice off. So when we get frost and ice on the top of the panels, that really curtails solar production. I have noticed that piece.
Okay. I do want to share with everybody, if you do have questions, we normally try to stop at 7, but we've got a little bit of extra time here tonight. So if you do have questions, please go ahead and ask them. We can go till about 10 minutes after if there's enough questions.
And like,
Go ahead.
oh yeah, I was gonna throw one out there and also kind of speak to Barb's question earlier that's in the chat. In the worst conditions, winter, frost on the panels, everything, or a really cloudy day, what effect does that have on how much energy you're able to generate, store, and dispatch?
Yeah, but again, the cloudy day is the amount of generation we have will really vary depending on how thick the clouds are. I mean, it goes all over the place. Was it yesterday we had some rain? Solar generation yesterday. Actually, we wanted to do some. We dispatched on Tuesday this week, and because the weather was hot in the south, we wanted to do a little bit of a dispatch over MISO peak on Wednesday, and Wednesday was pretty cloudy. And boy, we didn't get much charge at all. So under full charging, for example, I'll talk about Ramsey. The solar field there is 3.4 megawatts. We were literally getting 200 or 300 kilowatts of generation off that site all day. And wanted to dispatch some battery in the afternoon. We just didn't get much at all. So we dispatched what we had, but there wasn't much there. So that was some heavier clouds and precip. And off of a 3.4 megawatt system, we were getting 200 or 300 or 400 kilowatts of energy. On other days where no precip, but it is cloudy and maybe a little bit of sun coming through, we might get, say, 50% of nameplate capacity solar generation. So it really varies quite a bit. But on an intermittent cloudy day, it bounces all over the place. It'll go from 20 to 30% output up to full percent, or up to full nameplate, and back down to 30% again, and it'll just bounce up and down all day. It looks like a jigsaw puzzle. So it varies.
Yeah, thanks. Would those would those present any use cases where you'd charge the batteries from the grid like you described earlier, or is that just sort of a thing you could do but haven't put into practice?
We know we could do that, and like I mentioned, we've done that a number of times for testing purposes. We need to do some testing. We need full capacity. We're going to run a full capacity test here, and it's raining outside. This isn't going to work. Well, for testing, that's okay. We'll charge from the grid, discharge the batteries, make sure they work, and then I will just let Great River Energy know that we did that. So we have a commitment to NextEra to charge from solar for our demand reduction program, and also to Great River Energy. So if we ever do grid charge, we let them know we're going to do this. And then when we're done, we make sure and discharge all of the grid stored energy and recharge it back from solar, and then we're contractually whole. So yeah, grid charging, we can certainly do that. If there was a use case where we could charge from the grid in the morning when prices are cheap, and discharge again in the afternoon when capacity prices are high, to do some energy arbitrage, the batteries would be fully capable of that use case.
Great, thanks.
This is Chris asking. I think you partly answered that question that I was going to ask, and explaining again or reiterating the contractual arrangement, because I didn't quite understand when you explained it the first time about, I don't know, you were talking about the 75 cycles per year and resting
Sure.
50%. And could you just say it again? I think it's very interesting.
Absolutely. There's two pieces to the contractual operation. The ones you're speaking to has to do with life extension or life preservation, if you will, of the batteries. If you keep them charged up high all the time, or if they're empty all the time, that can actually do some degradation of their life expectancy. And if you cycle them a lot versus a few times, that can also add to life degradation. So in order to get as much life preservation and extend the life and the capacity of the batteries as much as possible, there are the operational limits, and that helps NextEra to keep their costs down. So if the batteries, if we just ran those things really hard and didn't have those boundaries, the batteries would degrade sooner, and they'd have to either replace some of them or add to the batteries. There's actually extra space in the container for adding to batteries as they degrade, but there's that cost. So those operational constraints help to preserve the life of the battery, and therefore less cost for NextEra, and that containment of costs is passed on to us in our energy services agreement.
Okay, I get it. So if you go over, if by going over the limits that they've set, you are essentially costing them money by degrading the battery sooner, they will pass a charge on to you that's extra.
Yes, we'd have to go back and say, you guys are running these too hard. We need to change the pricing or issue a penalty or something like that. Now, with those operational constraints, we've never come close to exceeding or even meeting any of those. As a matter of fact, we're allowed 75 full cycle operations per year. I don't think we've ever gone over 40 or 45. And so in the wintertime with that crazy snow, what we've been able to do, rather than, I mentioned that we have to keep them at 50% state of charge and not fully charged any longer than a 24-hour period. Well, NextEra has allowed us to actually charge those up 2 or 3 days ahead of time and let them sit there and count that against the cycles, because we just don't use all our cycles up all the time.
That's great.
We've been able to do some negotiating. Yeah.
Thank you.
Yeah.
Hey, Tom, quick question. Was there any consideration of bifacial solar panels?
Oh, great question. Not on these. Now, I don't recall that those were even looked at for this when we put these together. But the single axis tracking sites that we have are bifacial. I forgot to mention that. And so there is additional generation off of those panels, given that they're bifacial. And interestingly enough, the percentage of generation from the backside of the panel with respect to the total capacity is higher in the wintertime than it is in the summertime because of the reflection off the snow.
Yeah,
point.
that's why I asked that question. Yeah, another question that I had, when you guys went out to work with various organizations to put this together, were there organizations out? I mean, was there like 3 or 4 companies you could work with, or is it a very small group that are doing things like this?
Oh, we sent requests for proposals out to a number of suppliers, both for storage and solar. Of course, there was more solar companies out there than there were battery companies. And the number of battery companies, especially in the US, was fairly limited. Most of the battery material itself is not US produced. It comes from overseas, from China. And as a matter of fact, the batteries that are in the containers we have are from a company called Lithium. They're Chinese. So when NextEra put the systems together, they went out and worked with a number of suppliers for the inverters, for the cabling, the controls, for the battery modules themselves, and the whole bit. And they actually orchestrated and put the whole container together from sub-suppliers. So anyway, once we went through the bidding process and decided on the finalists who we're going to partner with, then we're down to just solar and storage, one each. And they went out and hired their own contractors to do the construction of the solar and of the storage. We, of course, worked with them. Our crews worked with them on the interconnection piece. But once we got down to making the final selections, then it was just NG and just NextEra.
Okay. Chris had a quick question of what is the brand of solar panels?
Oh, I knew somebody's going to ask that. I think they're Canadian. I should know that off the top of my head too. And I don't recall right off the top of my head.
Okay.
Might be able to look that up real quick, or I can send it to you.
And Patrick had a quick question too. Was the flow battery even considered on this project?
Not for this project, given the use case. The flow battery, of course, will take up a lot more physical space than the lithium ion does. The lithium ion is very fast reacting, and especially to do some of the voltage control, that type of thing, we needed a pretty fast reacting battery for that. Lithium is very good. And so given its size, given its energy capacity and availability and pricing, and also with the experience of what materials are out of the market, lithium ion was our choice.
Okay. And the final question from our scientist, Barbara, is, does the 75 cycles per year mean that you don't use them 290 days a year?
That would be correct. That would be correct. So that goes back to, again, our use case is demand response. So we are forecasting what one day it is per month that is going to be the system peak for the month. That's when we need to operate. Now, we operated this last Tuesday because it was really hot. It's going to be really hot again on Sunday and Monday and next Tuesday. Which one of those days is going to be the peak? Well, we operated last Tuesday because the weather could change and maybe that hot doesn't end up being that hot. Or maybe next Tuesday or Monday is going to be the hotter day. So when we look at a whole month, it's hard to forecast what day it's going to be. It might be Monday last week, it might be Tuesday next week, it might be the following week. So we have to plan to operate multiple days per week in order to make sure that we're operating that 1 hour when the actual peak happens. On average, that's about 3 operations per month, 3 to 4 operations per month on average. So that is, less than 50 operations per year. And that's just 1 operation per day. So in that respect, yes, all those days per year, we do not operate the storage. Now, the solar, of course, is running full time, and we're purchasing the power from that all the time. There's the radiance. But for storage, yep, they just sit there most of the time.
Okay. And maybe we'll end on this. One of our people that was on tonight said, excellent, many thanks. I'm a Connexus customer, and I'm very happy to see this work. We need to convert renewable energy as soon as possible. So with that, I just would love to thank you so much for your presentation. It was excellent. And I think everybody enjoyed it. And if people have questions, they can get in touch with you. Thank you, Tom. And we'll be, putting this up on a video in the near future on the MRES YouTube site.
Right, very good. Thank you all very much for attending and for the opportunity. And I'm a little embarrassed. I can't remember the brand of the solar panels or how many panels are in a string. So whoever is asking those questions, please grab my email address and let me get your email address, and I'll get those answers out there. Or Doug, I'll send them to you and you can disperse them to the group.
Yeah,
I
that'd be
will
great.
find those out. I should have known that off the top of my head, and I just don't recall. So we'll get it to you.
All right. Well, thank you so much again. And we'll talk to you in the near future about the Eco Experience event.
Yeah, that sounds like fun. That would be great. Okay.
All right. Thanks, Tom.
Thank you all. Yeah. Good night.